challenge problems to the reporter, please. The opponent, please challenge question, please.
We challenge droplet microscope, problem 2.
Wow, okay. So now please write down the names of reporter, opponent, and the reviewer. 各位老师麻烦自己记得签名，然后麻烦写一下选手的姓名。
应该对跟你这个差不多。对。没有，它是一个女一个猪，然后显示。
如果是5个许德瑞，他们写成谁的1块写下？许德瑞的上限大概是1派到9派左右。就那个许德瑞的不错，那就是找一些这种。
So the reporter, please, you may begin.
Good evening, everyone. I'm the reporter from Team 2. I'm going to introduce my report, and the topic is droplet microscope. This is the problem. By looking through the simple water droplet test on a glass surface, one can observe that the droplet acts as an imaging system. Investigates the magnification and resolution of such a lens. And this is the experiment to observe the dots which under the water droplet. And this is the method. First, make the simple microscope. Second, draw black dot on the lower transparent plate and draw water straw on the upper transparent plate. Third, see black spot through water droplet. And this is the experiment result. Based on the experiment, it is evident that a water droplet can act as a conveyor lens. Furthermore, during the experiment process, it was observed that the more water added, the greater magnification is, as shown in the diagram. The water droplet on the left side is 0.5 centimeter thick, and the right one is 1 centimeter thick. Both water droplets have same shape, but the one on the right is more convex, and the black spot is larger. And I'll first focus on the magnification. This is my theory and papers. The water droplet is like a conveyor lens. So I will use the lens maker's formula and thin lens formula to work out the focal length and magnification of the water droplet, and design experiments to verify the calculated data. This is the lens maker's formula. Use a linear ruler to measure the radius of curvature of the water droplet, and then use the lens maker formula to calculate the focal length of the water droplet. The reflective index of the water is 1.33, and the radius of the curvature is R1 and R2. R1 equal R2 equal 0.15 cm of centimeter. And I figure out the focal length is 0. centimeter. And this is the thin lens formula. Use this formula to find out the magnification. In the formula, P is represent the object distance, and Q is imaging distance, and M is magnification. And the data is shown on the table. And this is what I decided. This is the experiment I decided. I use the water droplet to observe the imaging of the object and find the focal length. The method is first set up a water droplet and place an object behind it. Third, place a plain carbon cardboard at the end of prevent the background from being too confusing and affect the observation result. In the end, place the phone and tripod 20 centimeters in front of the side and record the result. And this is my experiment discussion. an object is 0.5 centimeter away from the water droplet, imaging is an inverted, enlarged real image. Because the color order is inverted, the right color order is gold, orange, blue, and red, while the imaging is inverted. And then, when the object is 0.3 centimeter away from the water droplet, imaging is an inverted, enlarged real image. The color order is still inverted. But when the object is 0.2 centimeter away from the water droplet, imaging is an upright magnetic brighter imaging. The imaging only shows the orange side because the object is too close to the water droplet. And this is my experiment result. According to the result above and trying many times, I can make sure that the focal length is about 0.2 cm. This outcome is close to the result of the formula. So I think the focal length is 0.2 centimeter when the radius of curvature is 0.13 centimeter. And this is the experiment 2. I use the water droplet to observe the magnification of images. This is the method. I first set out the water drop and place a pad which see the object behind the water drop. And then place the phone and tripod 20 centimeters in front of the siren and record the result. And this is my experiment 2 discussion. When the object is 0.6 centimeters away from the water droplet, the magnification is 1 second because the length of imaging is half the length of the object. And when the object is 0.5 centimeters away from the water droplet, the magnification is 2 seconds because the length of imaging is 2/3 of the length of object. And when the object is 0.4 centimeters away from the water droplet, the magnification is 1 because the length of imaging is as long as the length of the object. And when the object is 0.3 centimeters away from the water droplet, the magnification is 2 because the length of imaging is twice as long as the length of object. And this is my experiment result. According to the result above, by observing again and again, I verify the result of the formula. And I'm focused on the resolution. This is my serious and focus. This the fraction of light can make 2 light sources overlap. When the central bright thing overlaps by more than half, there is a minimum resolution angle. And I focus on the angular resolution. And this is the formula of the angular resolution. Lambda is represent the wavelength of the light source, and D is the aperture of the transparent open. The formula indicates that as the aperture becomes smaller, the resolution increases, and as the wavelength becomes longer, the resolution also increases. According to the formula, we can use it to figure out the resolution of the water droplet. When the wavelength is 150 nanometers, and considering the aperture as the diameter of the droplet, and I use the radius of the droplet used in the previous experiment, multiplied by 2, so it equals 0.3 centimeter. We can get the angular resolution, which is 2,245.33 nanometer. And this is my conclusion. The result of experiments of 1 and 2 is almost equal to the outcome of formula when the object acts as an imaging system. And according to the formula of angular resolution, the smaller the object is, the higher the resolution is, and the longer the wavelength is, the higher the resolution is too. That's for the reason.
Okay. So now the opponent may ask questions to the reporter. You have 2 minutes.
Okay, so first of all, I want to ask about the experiment. Do you make sure that the material you use throughout the experiments from 1 to 3 are all the same? Yes, the material, like where you put the droplets on. Okay. So next question. Do you make sure that the droplets as you drop during the experiments are like the similar sizes, like shapes?
Yes.
Okay.
The radius is 0.16.
Okay. Okay, next question. Do you define the shape of the droplets of different volumes? Okay. Next question. Do you consider that the lower parts of the droplets, because we observe at lower volumes there's an inwards curve at the bottom of the droplets. Do you consider that part to affect the results of your experiments?
Can you say that again?
Okay, so at lower volumes, the droplets on the lower side will have inwards curves. And do you consider that as a factor in your experiment?
I don't think.
Okay. And next question. Are you sure that the focal length is the same throughout the experiments?
Yes.
Okay. Even when the volume changes?
The volume change, the focus change too.
Okay. I think that's it.
Okay. So the opponent will have 1 minute. So have 3 minutes. Okay. For discussion. So the opponent may proceed.
So I'm gonna be reviewing. I'm gonna be talking about problem 2, droplet microscope, and this is our problem statement. And their main focuses are the angular resolutions and calculations of the focal lengths and magnification. And I think their advantages are clear presentation and clear experiment setup explanations, and also deep discussion about the results. And our suggestions are more details of the definition of the droplets, like sizes and like the radius or something like that. And second, more factors should be considered, like the evaporation rate and so on and so on. And in theory, they use the lensmaker's formula for the thin lenses, and they also use the thin lens formula. And for their setup, they use a droplet as a simple microscope and experiment on metal pot and observe the object through the droplet. And the parameters, and it's the distance between the droplet and the observed object. And for analysis, they analyze the magnification through different lengths and see how it changes. And our point of discussion is first the droplet size. How do you define it? And second, how do you define the curvature of the droplet? And third, the lower parts of the droplet should probably be considered, and we'll be discussing in the next session. And fourth, the focal length. Does it change as the volume increases, or it just stay the same? The fifth, the calculate method of the magnification, because they only stated it about once and never talk about it anymore, and assume that's the magnification. And sixth, the evaporation rate, because at lower volumes of droplets, the droplets evaporate faster. And seventh, the changes in resolutions, because as the volume increases, resolutions might change as the magnification and focal length alters. And that's it. Thank you.
So the opponent may go ahead, ask questions to the reporter.
Okay, so let's turn to a page of the droplet size. Okay. Can you turn to a page that has okay, it's fine. So. This is a droplet, right? Yeah. Or is it more chocolate? Like this, right? Oh, so this is a droplet, right? Okay. So when it's like this, what are okay, you calculate the focal length using the magnification, right, and how it forms, how the image forms, right? Okay. Do you consider because in your first experiment setup, you say you put the droplet on a glass surface, is that right? Okay. So this is the droplet, and we can split it in half. And so, what do you think about the length about in the middle? Does it affect the magnification in the focal lengths? Or does it not really matter? Okay, so what about the lower points? When it curves inwards at lower volumes, do you think that would affect the focal lengths? Okay. So, do you try different volumes of water droplets? Okay, so you didn't consider like when the volume changes and how the focal length and magnification will change, right? That's right?
Yeah, because it's difficult to control its shape.
Okay, so when you are collecting data for your experiment, okay, you discover how do you make sure that all the data are like similar to this one, like they don't have like any strange phenomena. Yeah, that's the formula. Like you define the theoretical shape of the droplets. But what I'm trying to say is, how do you like select your data? No. How do you select your data? Because you said it that it's hard to control like how you drop the droplet, right? Okay. So then, when you're collecting data for an experiment, how do you make sure that they are the ones that you're looking for? You choose the best suitable ones. Okay, so next, can we please turn to the Siemens, the lensmaker's equation. Okay, so what are R1 and R2? Yeah, like there are two curvatures. Which one is which? Okay. So, but that's like different things because you said it first, like this is one of your experiment setup, right? Like you drop the droplet on your glass surface. And this is your other experiment setup. And how this lens-maker's formula, this definition applies to both. Like where is the R1 and R2 for this version of your experiment? Okay. Next, what about the curvature of the droplets? Do you consider it in your experiments, like when you're calculating the focal length or magnification? No, I mean the curvature itself. It's the radius of the curvature, and we use the radius of curvature to calculate the curvature. And for that, I want to ask you something, and it's about the definition of your shape. Do you think it's a sphere shape or an elliptic shape? Okay, so I mean this one, okay, the first one, the below one, where you drop the droplet on the glass surface. Yes. Do you consider it an sphere shape or an elliptic shape? Okay, so if it's a sphere shape, do you like consider the fact that the radius of it changes, like it's hard to, okay. So how do you calculate the curvature using the radius of the curvature? But then what's the point of putting in the radius of the curvature when you're not going to use the curvature? You just want to observe the phenomenon, right? Okay, so can we go to the experiment 1 analysis? I mean analysis, like discussion. Next week, please. Go backwards. Yeah. Okay, so let me just ask. How do you apply your theory data to your experiment data? How do you compare those and how they apply to each other? Okay, so you got your theory data, right? You have the theory, right? And you have, like, let's make a formula to calculate the theory, like the focal length and stuff. And how do you make sure that all these factors, all these like data, they are the same in the experiment, and how you compare those together? Pardon? Like, I don't understand. Can you say it again? Your experiment. Okay, can you enter the data? Can you enter the diagram for your first experiment? The diagram, the picture. The graph. Okay, whatever you need, they have that. So, how do you describe the relation between your theory focal lengths, like, and magnification to your experiment results? So, okay, so you do connect your theory with your experiment, right? Okay, so our suggestion is that you can probably add a graph to show the relationship between them, because it's kind of confusing when you're just saying it in some words. So next, I'm going to be discussing about evaporation. Okay, so we know that when the droplet is at smaller volumes, it evaporates faster. And do you think that affects your experiment and how it will like make the results different? Okay, so you know evaporation, right? Like the water will slowly loses its volume and then eventually disappears. It's like boiling water, and it eventually disappears, and that's called evaporation. Okay, so when the droplet is at lower volumes, it evaporates faster. And do you think that affects your experiments? But how do you make sure that evaporation doesn't like change the droplet shape, or like even make it smaller?
Okay. I think it's about time. So please, the opponent, please make your summary. 1 minute.
Okay, so we discussed about the definition of the droplet shape, and their answer is that they, for their two experiments, one they use, one it's defined as a sphere shape, and the other one it's unclear. And for the focal length and magnification, and they used the thin lens formula, which probably didn't take into account of the lengths between the two curves of the droplets, and they also didn't consider about the lower parts of the droplet, which might affect the magnification and the resolution. And also, they didn't consider about the evaporation rate, which how and why it will affect the droplet shape and all the data that related to it. And lastly, they didn't have a clear definition of the notations used in the experiment, in the series. Thank you for listening.
Okay. Now the reviewer, please get up and ask your question to the reporter and the opponent. You have 3 minutes.
Okay, so first to the reporter, I want to ask, did you put the droplet on the glass? Or did you just hang in the air?
In the front.
So, what do you want to get from your first experiment? I mean, did you get any data from this, or did you just
No, I just want to.
quickly?
I just want to observe the photo.
Okay, I see. So, you use the second way. So it's like you hang the droplet in the air to get your data. And for the opponent, I want to ask, did you ask the reporter about how they get the data?
You mean how they get the radius?
Yeah.
They said they use the lens maker's formula to calculate. It's not really they didn't mention it and I didn't ask it. That's fine.
So you did not ask?
Yeah, I did not ask it, but from their experiment, I assume that they just measured it.
Okay. Then I want to make sure, how did you get the radius?
I use the vernier tool.
So you did. Okay, so you use a ruler to measure. I think that's all. Okay.
Okay, so now you reviewer have 2 minutes for the preparation. Okay, the reviewer, you have 4 minutes to present your idea. Okay. It's counting.
So first, to summarize, they use magnification and also the resolution formula to try to observe their results. Okay, so first for the reporter, I want to first talk about their strengths. So their presentation is well and quite fluent, and they did answer the question, so the magnification and also the resolution of the droplets. And for the areas of improvement, first, the data is not enough, and second, they don't have enough charts, so they only used some words to express. And they did not place the droplet on a glass. I mean, they did at first, but they did not observe any data from this. And actually, this is what the question wants. Next, they did not compare the data with their theory. So they just put it in the theory and said that it's the same. And they had a misusing of resolution by figuring the resolution as an ideal lens, and misthinking on the non-uniform of the drop. And also the angular resolution should be an angle but not a lens. Okay, for the opponent, they presented really well, and their sound is loud, and they clearly ask their questions. For the areas of improvement, they did not mention that the reporter didn't done the experiment, which is to place it on a glass surface, and also they did not ask how the radio was meant. Okay, so for their discussion, they first talked about the droplet size. And for the opponent, they think that they want to know how they control the radius of the droplet. But the reporter did not have a great answer. And for our opinion, we think that the radius of the droplet will affect the results. And then for the next one, the opponent thinks that the radius cannot represent curvature. And for the reporter, they only figure the curvature by radius. And for our opinion, we agree with the opponent, which radius cannot represent the curvature. Okay. And the next one about the evaporation. The reporter thinks that the evaporation does not influence the results. But for us, we agree with the opponent, which we think that the evaporation will influence the results. Okay. And that's all. Thank you.
Okay. Now the floor goes to the reporter. You have 2 minutes to address your audience. Counting.
temperature to connect the parent and the materials, and add more data and announce the data.
Okay. So now please the reporter, opponent and reviewer please stand up and ready for the question from our jurors here. So any question from our jurors? Well, go ahead.
The reviewer just said that the radius cannot represent curvature. So what do you think is the relation between radius and curvature? The question proposal.
Proposal, okay. So I think for radius to use radius to calculate the curvature, I think there should be a clear definition of the shape of the droplet, because in a sphere, if it's a sphere shape, and the calculation of the curvature will be different from the ones that are used in the elliptic shape. So therefore, that requires a definition of the droplet shape in order to define the curvature calculated.
If it's a sphere, then what's the curvature?
Oh, it's 1 divided by the radius of the curvature.
Okay. And for us, we do not agree with the reporter because I think like the mass of the droplet itself will impact the curve. Like you cannot just get the curve from the radius because it might speak. Yeah, it's not a perfect.
But if you are given a curve, then how do you calculate? How large is the curvature? If you are given a spherical surface, how large is it?
If it's a smooth surface.
Yeah, so suppose you have a sphere, then how large is the curvature? Do you know that?
1 divided by the radius. May you please
What's
explain?
the connection between the radius and the curvature of a spherical surface?
Okay.
On the stage, the depth. We analyze that, so we only consider one direction, not two directions. If this is the droplet, we only consider this side, not this side. So we only need to, if it is a sphere, we only need to say the curvature is the 1 divided by the radius. If it is a sphere, but it's actually it won't. Okay.
So any other question from jurors? Go ahead, just go ahead.
Question to the opponent. So, what is this about the evaporation? So, what's the time scale about the measurement you are talking about? Like when you consider evaporation?
You mean what affects? What evaporation affects?
No. What's the time scale of the measurement?
Oh, it's around 100 milligram per second for the water.
No. Just like how long do you do the measurement?
You mean like
this? Like if you want to measure the shape of the droplet.
I would say like below 10 seconds would be best because
Below 10 seconds.
yeah, because after that the evaporation rate it won't increase, but over time it adds up to a large amount, and therefore it might change the shape of the droplet and affect the experiment results.
But you say below 10 seconds.
Yes.
And so what's the evaporation below 10 seconds?
Yeah, I said that it's like 100 milligrams per second.
100 milligram. Okay. So what's the weight of the total droplet?
We didn't measure that.
But I mean, if you want to consider evaporation, that means like you have like a substantial amount of
Yes.
mass loss during this less than 10 seconds, right? So you need to have the total mass.
Therefore, when like we are accounting for the evaporation rate, it's not enough. There's not enough like data to be discussed. in this report.
But you need this math math to say that
Yes.
like evaporation need to be considered.
Yes.
Okay. Any other questions? Okay. If you don't mind, I think it's over for now. The juror now will calculate the score for each team. Okay, you may see. You may see this. So I think we are all ready. So now we first present the score for our reporter. Okay. Okay. Show them the scorecard. 4, 5, 5, 3, 3. Okay. Now for the opponent, right? Okay. Let's wait for a moment. Okay, 6, 7, 7, 7, 5. Okay. Now, finally, for the reviewer. Okay. 6, 6, 7, 6, 5. Okay. Any comment from our juror here?